Microclots, let's talk about that for a moment, because they are not your normal clots. So normal clots form when you have a cut, you have a wound, and what happens is you have this molecule in your body floating in your blood called fibrinogen, and when there is a wound, what can happen is this molecule thrombin will cut fibrinogen, and fibrinogen is water soluble, and then once it's cleaved by this molecule thrombin, it becomes insoluble and it can start forming clots. So these clots are like tiny jelly pads, is how I think of them. And what happens is they're going to be small in size, maybe 100 micrometers, and we'll talk about these sizes in a moment as well. And what happens is, of course, they can be dissolved easily once their purpose is finished. Now those are natural clots. Now these microclots, they are very different because they are not easily dissolved afterwards. They actually, what happens with them is once they form, because of how they form, they can persist, and they're very hard to destroy. Now, why is this? Because these clots are unusual because they are what these authors refer to as amyloid microclots. Now, I need to tell you a little bit now about amyloid proteins. Now, what does that mean? It's a form of misfolding of a protein, but it's a very specific type of misfolding. So all of amyloid proteins are misfolded proteins, but not all misfolded proteins are amyloid proteins. Okay, do you follow? Now, what happens is in protein, remember, proteins are made of amino acids. Genetic information is the blueprint that tells you how to produce a protein. Then special machinery can read genetic information like mRNA to produce a protein. Protein is made out of amino acids, and then amino acids have their electrostatic interactions. They can start interacting to start forming three-dimensional shapes. And there's three distinct forms of shapes that proteins can use in order to complete their three-dimensional structure. And that is alpha helixes, so they're helix like in the DNA. And the other one, there's also undysregulated loops, so floating fragments of chain of amino acids. So those are loops, they're very mobile. And the last one is what is referred to as beta strands. And this is where amino acids make like a zigzag line back and forth, and when you have enough beta strands, you can form beta sheets. And these beta sheets, because of atomic arrangement of the atoms that make up the beta sheet, attracts other beta sheets to it, and beta sheets can start stacking on top of each other. They're very highly attracted to one another, and this is exactly what happens with amyloid proteins. So with amyloid proteins, what happens is they get misfolded, and their beta strands will come out into the open when normally they'll be buried somewhere deep in the structure of a protein, and then they can start forming these beta sheets, and they can attract other proteins as well. And that's exactly what happens with these microclots. They are often made up of many different misfolded proteins together. So it's not just fibrin or fibrinogen, and thrombin is not even necessary for this clot formation. So you can forget about thrombin, you don't need thrombin, and these clots can form because of the misfolding of proteins. Okay, so that's the microclots in its nature, and that's why they're so resistant to degradation afterwards, is precisely because of this strong electrostatic interaction between these amyloid components, these beta sheets. Okay. All right, so that's your microclots in a nutshell, but you'll see in a moment that micro might be a bit of a misnomer too, in my opinion, but you'll see that in a moment. Now, there's one more thing that I want to introduce to you before we're going to start exploring these deeper, is this compound called thioflavin T. And thioflavin T is this molecule, it's a chemical that can go and interact with these beta sheets. So when you put this molecule into the solution where you have misfolded proteins or these microclots, thioflavin chemical can go in there and interact with these beta sheets. And because it's specific to beta sheets and misfolded proteins, it shows you right away it's a marker that to discover these misfolded proteins or microclots. And because when it starts to interact with the misfolded protein beta sheets, it becomes sensitive to the specific light wavelength, and if you fluoresce this wavelength on it, then it will start fluorescing. So it's very easy for this group of scientists to spot microclots in the blood, because they just have to add this chemical and boom, the microclot will literally fluoresce, and we'll see that right away, because that's the first image I want to show you from this latest paper. And you can see they show you two images. They show you image under regular light, so you see these microclots what they look like under regular light, and then next to that you see corresponding image of when you add this chemical, thioflavin T chemical, that makes it fluoresce, and you can clearly see how it would look like when it fluoresces, right?